Hello everyone, and welcome to Organic Chemistry. In this lecture, we will begin Chapter 1, a review of general chemistry, electrons, bonds, and molecular properties. This chapter reviews important concepts from general chemistry that will serve as the foundation for the entire course. Throughout organic chemistry, we will constantly focus on electrons, bonding, molecular structure, and how molecules react. At the end of the chapter, I hope that you will be able to first compare and contrast organic and inorganic compounds, identify and describe constitutional isomers, define the terms covalent bond, valence electrons, Lewis structure, octet rule, and lone pair, define the term formal charge, and describe how formal charge is calculated. In addition, define the terms of electronegativity, nonpolar covalent bond, polar covalent bond, ionic bond, and electrostatic potential map, and describe how to locate partial charges. Demonstrate how to read bond-line structures by converting other styles of molecular representation into bond-line structures. Describe the shape and phase of s and p atomic orbitals and the process of filling orbitals with electrons. Demonstrate understanding of a valence bond theory by using it to define a bond. Compare and contrast molecular orbital theory, valence bond theory, molecular and atomic orbitals, highest occupied and lowest unoccupied molecular orbitals. Explain how pi bond, sp3, sp2, and sp hybrid orbitals sets are formed. Explain VSEPR, identify molecular dipole moment, describe basic nature of all intermolecular forces. Lastly, compare the actions of soap and dry cleaning in removing oil or grease, and explain how drugs and receptors bind together. As you can see, many of these concepts that we will be reviewing you have already seen in general chemistry. Now, as a brief introduction, organic chemistry is the study of carbon-containing molecules and their reactions. What happens during a chemical reaction? Molecules collide. If they are close enough, they carry enough energy, and the electrons that interact are in an advantageous position, then you see a transfer of electrons will allow for bonds to break and new bonds to form. This is one of the major questions in organic chemistry, which is why do reactions occur? The answer ultimately comes back to electrons. Throughout this course, we will focus heavily on electron movement and bonding. You see these little arrows. You will see a lot of them throughout the course, and what they are representing is the movement of electrons. So they go from, you see this electron lone pair right here, to here. These two electrons in this bond, they're moving here. They represent these two electrons here and these two electrons here. So always focus on those electrons. Why do we distinguish between organic and inorganic? Well, because organic is such a rich area, and everything carbon containing is such vast that even making it into its own subdiscipline is still a fairly large amount of material. We distinguish organic compounds from inorganic because organic compounds contain carbon atoms. Organic compounds are extremely important because they make up many of our everyday items such as food, clothes, pharmaceuticals, and plastics. Carbon's ability to form multiple stable covalent bonds allows it to create a huge variety of complex molecules. You can see here, for instance, you can also go from an inorganic component to a highly organic component such as ammonium cyanide into urea. In the mid-1800s, it was first suggested that substances are defined by a very specific arrangement of atoms. A molecular formula alone was not enough to define a compound. Why? Well, because compounds can differ in very specific ways, specifically how their atoms are connected. Compounds with the same molecular formula but different structures are called constitutional isomers. This is important because different structures can produce very different chemical and physical properties. You see here two structures with the same chemical formula. One of them is dimethyl ether, the other one is ethanol. And as you can see, some other physical properties down here listed at the bottom. The atoms most commonly bonded to carbon in organic chemistry will include, but are not limited to, nitrogen, oxygen, hydrogen, and the halogens, that group 7A, fluorine, chlorine, bromine, iodine. With some exceptions, each element generally forms a very predictable number of bonds. So if you're binding carbon with oxygen, you can expect oxygen to form 2 bonds or a double bond. Nitrogen will be 3, carbon will be 4, etc. A covalent bond is a pair of electrons shared between two atoms. In the example that we see here, the electrons are shared in the space between two atoms. You can see these two hydrogen atoms coming together until you form a hydrogen molecule. Typically, there is a competition between repulsion of like charges and attraction of opposite charges. Once you reach that equilibrium of charges, that lowest point of energy, that's where the bond is stable. You can see here, this is the bond length optimum for the case of hydrogen. We can make this calculation for every type of bond that exists. How do potential energy and stability relate? Chemical bonds involve both attractive and repulsive forces. The attractive forces occur between positively charged nuclei and negatively charged electrons. Repulsive forces occur between the two nuclei and between the electrons. The bond forms at the distance where these forces balance and the system reaches its lowest potential energy. This is a review from general chemistry. Protons and neutrons reside in the nucleus. Electrons occupy orbitals outside the nucleus. Valence electrons are the electrons in the outermost shell. These valence electrons are especially important because they are involved in bonding. Typically, when we talk about electrons in any chemical reaction, more often than not, it will be those valence electrons. You can determine the number of valence electrons by analyzing electron configurations. For group A elements, you can also use the group number on the periodic table. The group number corresponds to the number of valence electrons. For simple Lewis structures, we can draw the atoms, represent valence electrons with dots, and allow atoms to share electrons to complete octets. In ammonia, for instance, nitrogen forms 3 bonds and contains 1 lone pair of electrons. You can see nitrogen has 5 valence electrons, sharing these 3 electrons with each of the hydrogens here in the scheme will allow nitrogen to be surrounded by 8 electrons. And as you recall from general chemistry, hydrogen does not need to be surrounded by 8 electrons, it only needs to be surrounded by 2 electrons. The process of drawing Lewis structures remains the same. Count valence electrons, arrange atoms, share electrons, and complete octets whenever possible.